Anyway, thanks for having me. It's a great pleasure to be here. This today is a purely applied paper, but Matthias said this is fine and okay. It's joint work with Tomás de Mayo Castro from Palma and Álvaro Escribano from Madrid. And we have data for some climate variables of the Earth and temperature, ice volume, and CO2 to be exact for the last 800,000 years. And we try to model this data. Basically, what we try to do is to identify possible cycles which are in this data and try to link these cycles to global Earth variables, which are cyclical anyway, and try sort of to find a link which of these Earth variables really drive the climate variables of the Earth, and try to link these two things. This doesn't seem to.
Yeah, you have to click into the slide parameter.
Okay.
So now it should work.
Wow. Okay, that's the plan. First, I'll tell you a bit more about the data. Say something about our model selection procedure, which actually comes from a different paper, the way in which we apply to identify the cycles in the data. We talk about cyclical co-integration, and in the end, we try to do a forecasting ways with other models and see how our model behaves in terms of forecasting. Okay, this is something which you probably basically know, but anyway, there were always some type of climate change in Earth history, and climate change is usually linked to an increase of the global surface temperature. And as you also will see later, the settlement of humans about 10,000 years ago actually was sort of the first real human driver of climate change. But before humans interfered with temperature and other things, there were still huge changes in the Earth's temperature, and they were mainly driven by some orbital variables which influence strongly the global ice volume or the CO2 level and the surface temperature. And the idea of this paper is sort of is to link these orbital variables to these climate values. So this is basically, these are the orbital variables of the Earth. Believing that the Earth here is circulating around the sun, there are basically three main components in these orbital variables. The first is the eccentricity. The eccentricity basically measures that the Earth doesn't circle in a perfect circle, but in an oval, and the eccentricity measures this difference. This difference from a circle, from an orbit is a circle, more or less. So this is what eccentricity does, but this doesn't stay constant. This varies over time, and the cycle eccentricity produced is around 100,000 year cycle. So this changes basically every 100,000 years. The second one is obliquity. So this is the rotational axis of the Earth, and this just moves forwards and backwards, and it moves forwards and backwards every 40,000 years. At the moment, we are in a situation where the Earth is nearest to the sun in the winter and furthest away to the summer, and this will change at some point, and we are nearest to the sun in the summer and the other way around. And people believe that the way the Earth is tilted at the moment leads to rather a warm period, while sort of a change from the tilt is the driver for ice ages. So at the moment, we are sort of just in the opposite direction of the ice age. And the obliquity, this just moving around of the Earth axis, has the cycle of roughly 41,000 years. The third one is precession. I don't know what's the meaning. I think it's a spinning top in English or something, but those of you who have children know a Brummkreisel. If you just start a Brummkreisel, it starts moving perfectly symmetrically at the beginning, circling around, but after a while, you will see it sort of does weird movements and isn't straight anymore. And the same happened to the Earth. It was, I think, more or less perfectly circling around itself at the beginning, but now the rotational axis of the Earth makes also some weird, so it has some weird circulations, like the Wundkreisel does or Stringentop does, and these circulations of the rotational axis of the Earth is called precession, and this is a cycle of about 21,000 years, which it produces. So these are the orbital variables which we take into account. These cycles are also called methodological cycles for the Earth, and yeah, they actually change over time, but this in the time span we have, these are basically the time we have. Our data will show you a bit more in a minute. Is Paleoclimate data, which was gathered from cores drilled in the Antarctic ice cap. So some people drilled a hole in the Antarctic ice cap, and this statement is actually not 100% correct. This is true for temperature and for CO2, and I'm not a geophysicist, but what they do is they measure the amount of oxygen and CO2 in this ice core, and depending on the amount of oxygen and CO2, they estimate the global temperature and they estimate the CO2 amount some point, and they need an amount of ice to provide sort of a decent measure, which spans around 1,000 years of Earth history. So from this, we have data, each data point represents 1,000 years. We have this for 800,000 years. So basically, we have 800 observations for the last 800,000 years, and one observation is every 1,000 years. We also have ice volume, and although we claim it here, the ice volume we do not get from this Antarctic ice cores. We get this from some sort of mussels which live down deep in the sea, and you have oxygen isotopes which you find in their shells, and this is a proxy for the ice volume in the Earth. We got this data to pay the credit gratefully from David Henry and Jennifer Castle, and also to provide, you will see later in the forecast exercise, in comparison to their model, but actually this data is also pretty available on the internet. So we are not the first one using it. The first one connecting it to these methodological cycles was TRR. What we might also see somehow later is that it has been found that CO2 seems to lag temperature by around 600 years. And there are a lot of contributions who love playing around with this type of data. We have some integration analysis, we have classical regression techniques being applied, and James Davidson basically applied the whole econometric toolbox once to this data and showed all possible things like causality and other things, but they all concentrate sort of on the zero frequency periodogram. So they do not take into account cycles and cyclical behavior, and this is sort of what we try to add in this paper. We also have a forecasting exercise, and there were quite a few people doing some forecasting using either machine learning approaches or a vector regressive approach from Carsten and Henry, which is sort of the competing model in our forecasting exercise later, and some score-driven or deep-driven models to also use for forecasting. Right, this is the temperature series which we got. This is sort of 800,000 years. Temperature, as I said, don't ask me how people know, but this point 0 here is 1952. I don't know how they can date this, but if you look at the literature, they claim that 0 is 1952. We have to know this because we have to time the orbital variables for around 1952, and then basically every observation is about 1,000 years. Although I do not believe that the second one is 952 exactly, but anyway. What you see if you look at the temperature, which I personally find quite nice to see, anyway, is that around half of the time span at 400,000 years, there's some sort of change in the behavior of the temperature. So it's rather low here, and then suddenly something must have happened, and the temperature increases quite a lot, but this shock sort of dies out somehow. If you Google a bit, you find that there must have been some volcanic activities, quite a lot of disastrous volcanic activities, and you do not find many human remains in exactly this time span around 400,000 years ago. So this must have been really quite a disastrous event. What happened there? So in terms of human history, humans have been alive in some type of form of human existence for all of this time span, but really, in the way we would interpret human life, this is basically this last bit here. If you look at this data, it looks very cyclical, so there seem to be cycles in it. If you look at the autogroup variance function, it also has sort of the sinusoidal behavior, so this also looks like some cyclical behavior. And the temperature series has, the period one of the temperature series has peaks, which are away from zero, so this is also an indicator for possible cycles in this data. Similar is it with ice volume. Ice volume just looks the opposite way around from temperature. So if you have a high temperature, there's a low ice volume, obviously, and the other way around. Or what I forgot to say before, just this dashed line will be the point where we split up the data later for forecasting. So maybe you can remember this will be the out of sample period and this the in sample period later. So this is why you see a dashed line there. Anyway, you again see the sinus behavior of the autogroup variances, and you see peaks in the third one away from the zero, indicating once again for cycles. And not surprisingly, a similar observation can be made for CO2. So this is CO2. Again, it looks very cyclical, similar looking autogroup variance function, and the period one once again seems to have cycled and peaks away from zero. Our orbital variables are these. This is eccentricity, and to be quite fair, if you Google eccentricity, you will find a formula for eccentricity. So you can basically put in your time and then derive the value of the eccentricity at this point in time. So this is really a perfectly deterministic function. The same with obliquity and the same with precession. You can just compute the eccentricity depending on the Earth age you like and you want. So this is a perfectly deterministic function, but it looks rather complicated and with a lot of sort of cycles overlapping in here. This is why, or possibly why in the literature, usually also these orbital variables are treated as random variables. And we just think, well, this is nice for our purpose, so we just do what people before us did and treat this to be a random variable. Although, to be quite fair, you can just compute this just a very complicated function where you can get eccentricity from. But once again, you see some cyclical behavior here away from zero, and it looks a bit similar to what we have seen before. Obliquity with a 40,000-year cycle moves a bit faster, which we can also see in the autogroup variance function, and the peak is a bit further down here. So this also seems to have some cycles, and precession is the same story. It moves even much faster with a 20,000-year cycle. Once again, the sinusoidal autogroup variance functions and the peaks in the period one. Right, the first thing, what we did is to see if these cycles are deterministic. So we basically modeled them as a sinus and a cosinus function and saw if anything was left. And indeed, thus modeling them as a deterministic cycle doesn't remove all of the all of the seasonality in the data. So we think it is okay to interpret them as stochastic cycles because there's always something left. And I think the most popular model for stochastic cycles is the K-factor gamma model, which is the model we use also in this paper. was first proposed by Gray and co-authors and also by Delighted Diapos and Woodward. And basically what this gamma model does is it allows for several cycles, not just for one, but for several cycles, with also some persistence and different persistence parameters. So basically it splits up the model as an interim product of different cycles with different parameters of persistence. And then you have AR and MA parameter polynomials around this, so that you have sort of a model with possibly K cycles in the, possibly K cycles. This is the very general model, and that's most of the seasonal long-memory models which you find in the literature. And then also K stochastic cycles. If you you can write this model in an MA infinity representation, so basically it is a linear general linear model, and the coefficients of this representation would be the Gegenbauer of our polynomials. This is where the G comes from. So this you can write as a linear model, allowing you to derive the spectral density. The covariance function just looks like the covariance function of the long memory process with the hyperbolic decay plus some cycles coming from this cosine function. And the spectral density basically looks also like the spectral density of a persistent process, but now you just shift the pole in the spectral density. You don't have it just at the origin, you basically shift it to any other frequency. This is more or less the idea, and you allow for K possible poles at other frequencies on. We want to find now a model selection way of selecting a model which sort of estimates the number of frequencies. So we need to estimate the number of cycles of K. We need to estimate the position of the cycles, so the frequency gamma J where they occur, and we want to estimate the memory parameter little J. Right. We are not the first one who tried to do this, but basically all model selection procedures for gamma models assume that you know K, that you know the number of frequencies at least. And this is maybe what we suggest here is the way of estimating K in the first step, in addition to the frequency and the memory parameter. Woodward estimates the frequency and the D by using a grid search, and there's a test by Robinson who basically assumed different types of gammas and Ds and then tested whether these are the correct values or not. We want to test whether there are exactly, say, I or Ki frequencies or cycles in the data, and test this against the hypothesis that we have more than Ki cycles, and then basically we just go sequentially, start to test 0 against more than 0, 1 against more than 1, and so on and so forth, until we cannot reject anymore. So that if you find the correct amount of cycles, the difference model is just the white noise, for instance here. Whereas under the alternative, if we misspecify the number of frequencies, there are still some left, then you basically get still a gamma model, but with less cycles than you had before. This is more or less the idea of our approach. So, to show this graphically, this is a cyclical time series which has 2 cycles. You can see the cycles here in the oscillation function, but also you have one big peak here and one big smaller peak there. Our test will identify the highest peak first, wherever this is. So we first identify the maximum of the spectral density. We filter this maximum of the spectral density out. In this time series, only the faster moving cycle remains, and we have only one peak in the spectral density one left. So this one we still have to filter out, and this is what happens after filtering out all of them. nothing is left in the program, and we have the whiteboard process more or less. Okay, the idea is, as I said, to start with the assumption that we know that we have no cycles in the data, against the alternative that we have more than no cycles, so that we have any cycles, and then we repeat this procedure again and again by always adding up one extra possible cycle and reduce and filter out these cycles. Right. And then we stop our procedure as soon as we cannot reject this null hypothesis anymore. A test for this problem is actually quite old. There's Walker's G test, which does this, and we just need a modified version here. This, I think a couple of years ago, had this 100th birthday, this test, but anyway, so it's a pretty old procedure, testing for cycles in the spectral density. And I mentioned this procedure a couple of times now, but anyway, the idea is to see first of all whether there is a significant pole in the parallelogram using Walker's G test. Then we estimate the location of the pole, and we do this by taking the maximum frequency in the parallelogram, just the highest frequency. There are several papers showing that this is a consistent estimator. Unfortunately, for our climate application, this holds only for stationary processes, while we will see that these processes are non-stationary. But unfortunately enough, this year there's a new paper the other year who proved that the maximum of the parallelogram is also consistent for non-stationary processes. So this was just coming in time for our application. And there is a local Whittle type estimator by Adejo and Robinson. We just estimate from both sides of the pole the persistence of the cycle. So we remove this pole by applying this estimated filter and go on until we cannot find any further poles. Well, the idea of Walker's G test is basically to use the parallelogram and standardize or compare it with a theoretically assumed spectral density. And the G test is then more or less just this one here. It's the maximum of the parallelogram divided by standard deviation. And you can show, or we show in the paper, that we get this exponential type of limiting distribution for the test in our for the test. What we need to do is to find a consistent estimator of the spectral density, which we don't know, and the purpose was to find an estimator of the spectral density which is still consistent but as bad as possible, because we have some strong peaks. We want to identify these peaks as our relevant pole. But if if our estimator of the spectral density just makes the same movement of the piece, it just kills sort of the effect which we want to test. So we needed something which cannot see really the peaks, the poles, and we use just a spline type estimator for the spectral density, which seemed to smooth enough to smooth away the poles and don't see the poles which we are interested in, but still fulfills the purposes which we had here. Then we estimated the frequency, as I said, as to be the maximum of the parallelogram, and Yajima showed already in the 90s that this is consistent estimator, and for non-stationary processes, Abadir showed this year. And then we used a local Whittle type estimator for the memory parameter, the D, to estimate basically the memory parameter, which is this so it's a standard type of local Whittle estimator. It's just that when you have the poles and the borders of the parallelogram, you can just come from one side, either from the left or from the right, whereas otherwise you come from both sides, so you have to adjust for this by dividing by 2 if you are 0 or p by frequency. Okay. At the end, we applied this procedure to our climate series. And for the climate series, we discovered 2 cycles for temperature, 2 cycles for ice, and 1 cycle for CO2. And the frequencies which we found are nicely enough to 0.6 and 0.115 for temperature and ice, and 0.6 frequency for CO2. And I don't want to spoil everything, but this is exactly the frequency of eccentricity, and this is the one of obliquity. So we do find these 2 frequencies of the orbital variables, also temperature and ice. And now I spoiled everything. You see, for eccentricity, we found 5 cycles. 1 is this 0.6 frequency. Obliquity had 2. 1 is this 0.15. And precession had 1, this frequency of 0.26, which we cannot find actually in our climate variables anymore. So in our climate variables, we only find this one from eccentricity, which is exactly the 100,000 year cycle, and this one is exactly this 40,000 year cycle. And precession is not present. Nicely enough, we also find the 0 frequency for eccentricity, showing clearly that this 100,000 year cycle is not a 0 frequency, but it's a cycle. Which we thought is quite nice to see. So we saw that at least these 2 cycles are present in the climate variable as well as in the orbital variables, but we want to see if they are really linked with each other in the sense that they sort of drive temperature and ice volume. And this just summarizes what we just said. Okay, before I come to what it drives, this is to see the filter series of temperature. You see nothing is basically left in the filter one, so we filter all the cycles out, and basically nothing is left in the auto-covariance function. So we obviously got or estimated the cycles correctly. Okay, we wanted now to link, see if these cycles really are linked, and eccentricity and obliquity are driving temperature and ice volume. And we try to do this with finding cyclical cointegration relations between these variables. So we estimated a cyclical cointegration model between the orbital and the climate variables. To the best of my knowledge, at least, this is the only approach for cyclical fractional cointegration. So we applied this approach, but it has quite a few drawbacks. One drawback is that you can apply it only on 1 frequency, and you have to sort of filter out, first of all the other frequencies before you just consider the 1 frequency which you're interested in. It can only go for contemporaneous cointegration, and it's only bivariate. So these are the drawbacks we had to accept. And so we have to do a pairwise comparison. We have to filter out all the frequencies which we do not want to test for the cointegration first, and then we can see if we have some cointegrating relationships or not. And the test is just a standard t-test on the cointegrating vector to be 0. Right, the 2 frequencies we want to consider and look at is the one from eccentricity, the 0.06 frequency, and the one from obliquity, the 0.15 frequency. And what we find for the obliquity frequencies is that we have cointegration between temperature and ice, temperature and obliquity, and ice and obliquity. These were the 3 the 3 variables which share this frequency. What might be a bit counterintuitive is that the cointegration coefficient between temperature and ice is positive. You would assume that it's negative, so high temperature leads to lower ice volume, but this is cyclical cointegration. So this is a coefficient which relates to this specific cycle. And further, to be honest, I don't really have an intuition for this coefficient myself, but if you run the cointegration on the 0 frequency, the coefficient becomes negative if you would expect it. Yeah. So this is must have a different interpretation. Has obviously a different interpretation. If you do it on the 0 frequency, as I said, it's negative expected. not quite as nice, but still, I think, okayish are the results for the eccentricity frequency. We found them in temperature, ice, and CO2, and we have integration basically everywhere, but not between temperature and CO2 and ice and CO2. We would expect really to, first of all, having temperature and ice, finding the integration here, and CO2, and eccentricity and temperature and eccentricity everywhere integration. You would assume that you have integration here as well, but we applied, or we had a general sort of approach to integration in the sense that the Ds did not have to be the same for all of the frequencies, and then the co-integration space does not need to be unique. So it is possible that you get this outcome. Which you would assume also the temperature and CO2 are somehow co-integrated and connected. But first of all, the rejection is pretty close. So this is a two-sided test. If you do it one-sided, you can maybe reject and sort of play a bit around to get some co-integration on the one hand, and on the other hand, we just learned that CO2 is next temperature by 600 years. We have observation every 1,000 years. So the CO2 observation, which really belongs to the temperature observation, is somewhere in between, and we don't really observe we don't really observe the value of CO2, which should be contemporaneous with the temperature observation. So maybe this is a reason, or it just doesn't come out and it's not integration. But anyway, this is here what we find.
So if I understood correctly, the co-integration test is not the to me conventional one to test whether the residuals are less persistent than a unit root or than some other persistence fractional, but a t-test on the coefficient.
Yes, it's just a t-test on beta.
Which null distribution do we have to work with when
beta is 0, so no co-integration.
I mean, against which distribution do you compare the t-statistics, or which distribution do those t-statistics follow under the null?
As much as I remember, it's a couple of years ago, and my memory is also just a t-distribution.
So despite all these fractional things, like if we didn't have co-integration, that would be a spurious regression, and
no, we sort of have some. Oh God, it's some of this. No, it's not spurious. So it's no spurious regression. So you do some sort of difference in this sort of test. And then it's just, oh God, I should have read the paper beforehand again, but I think it's just basically a t-test on, on the beta quality. Yeah. Can we go? So. Right. After this, we wanted to use these results for forecasting exercise, and the problem is that you cannot really use the co-integration results because, first of all, they are for one frequency, and we had a lot of this was all a composition of many frequencies, and just using the residuals on one frequency from these co-integration results would not give usable or sensible forecasts. So we had to sort of go another route, and what we use, or the idea or the trick, is that there's a paper by Barnes and co-authors who just showed that if you have a high dimensional vector autoregressive process and you marginalize this here with n tending infinity, you marginalize this, then you then can mimic some of memory processes. And this is sort of the idea we try to use. We interpret climate variables to be a climate to be a highly complex and high dimensional process, and what we observe here is just the marginalization of this very complex process. But this Bowens paper is just once again the standard VAR model not allowing for cycles, and what I personally think is actually quite nice. What you will see is if you generalize this approach to cyclical processes, it turns out that you do not get a VAR1 but a VAR2. So what your autoregressive process order 2, because you basically come from both sites, and the order 2 is exactly what we actually find in the temperature model to be the correct order to model the data. So the approach we are basically going is to use our 2 model to do our forecasting approach. We use the results which we basically had from the analysis before. We put all the variables which seem to be relevant into a regression model. Then we did a generative specific approach to reduce the amount of variables to those which are significant. And then we use this model for our forecasting exercise, and we compared it with the model of Castle and Henry, which is just about 1 model. This is the model which came out. The cycles were modeled actually by cosinus and sinus functions to bring the cycles in, or those deterministic cycles, and this is how we approximated the cycles. Other than that, this is a completely linear model having temperature in it for the first leg, and because of order 2 for a second leg, we have ice in it, obliquity and eccentricity, and we also included at the beginning obliquity and left obliquity and eccentricity and left eccentricity. And it turned out that the coefficient for eccentricity and left eccentricity is the same. So we included the difference of eccentricity rather than these 2 legs, and checked whether there is some remaining whether at the sort of leg eccentricity there are some remaining values for this, or some explanatory power, but this is not the case. So if you add to this the leg eccentricity, basically the coefficient is insignificant. Whereas for obliquity, this would be the case actually. So this is why obliquity goes in as the contemporaneous and the lag value, and use this model for our forecasting exercise. The R squared is nice and very high, and as you see, the fit of the data is also very nice. The black line is the original data, and the red line is just what we fitted with our model, so no forecasting yet. Just the fitted data, and these are the residuals from our model fit. They also seem to be well behaved. The same for ice and for CO2. This is the competing model by Castle and Henry. They do not have, they did not take cycles into account, and they tried to model this by some nonlinearities. They took products of eccentricity and obliquity, products of eccentricity and precession. They had the square of obliquity in here, and also product, again, of eccentricity of obliquity. So they tried to circumvent this problem by nonlinear combinations of these orbital variables. Just to see which model fits the data better, we applied a Young box test, and you see the Young box test cannot reject the rule of white noise residuals for our model for all of the climate variables, whereas it does for temperature and CO2 in the Castle and Henry model. And this is actually because of the second lag, which they do not have in the temperature model, but we do. Both they are actually aware that they should have used the second lag in it, second order model, but they didn't. And you see that we really need it for a good model fit. And I think personally, I think it's quite nice when it comes out theoretically. You see it also in the data that you need the lag fit in that model. Well, this is what we then did as a forecasting exercise is, you remember the dashed line. We took the last maximum of temperature, which you have seen, and split the data there. Everything which was before the last maximum was the in-sample period, and then we did a forecasting exercise until the end of the data, which is roughly 125,000 years. So quite a long forecasting horizon, and we were hoping to find at least the turning points, which happened in the meantime. we did this with our model, and we did this with the Henry Castle model, and for all three climate variables, our least squared forecasting error is better or lower than the one of Castle and Henry, although it's actually pretty high in both cases for CO2. We performed the Debord-Mariano test, and this confirms that this is a significant difference. And this is the graph to our forecast. So here we have the example period, then we have the last maximum of temperature, and I hope you see the red line is our forecast, and the black curves are the confidence intervals. And we get the last turning point here quite well, so we more or less get these turning points. In temperature, we get them for ice volume and for CO2. And for all of these variables, the data lies nicely within the confidence bands. But then, oops, at the end of the observation period, you see that the data suddenly moves upwards and leaves the confidence band for temperature. It leaves the confidence band for ice downwards and for CO2. And this is exactly 10,000 years ago. So this is when humans started to settle. And obviously the beginning of settlement of humanity was the first driver of climate change, which is quite nice to see. Henry Castle actually had the same finding. The data suddenly leaves these confidence bounds, and we cannot predict this anymore. So this is maybe a first indicator of early climate change before any industrial revolutions.
Quick question, how did you set up the forecast intervals?
It's comes from the Wahlkrumm model.
Okay,
Yeah, it's basically just sort of from a normal distribution left to right.
okay, so it's conditional,
Yes.
sorry,
Yeah.
forecast plus.
Forecast plus 5% interval.
Okay.
Yeah. And finally, we tried an out-of-sample forecast. So we had the orbital variables for the next 100,000 years. So we started basically today on 1952 and forecasted the next 100,000 years. This is the red line, which you see basically here, and you see what we do estimate. First of all, or predict is that we are now in the turning point. The temperature should move downwards. This is actually what people generally, I think, believe, and which can be confirmed. Here, for ice, it goes up, and for CO2, it goes down. So if there would be no industrial revolution, nothing would be industrial climate change these days, we should observe a decrease of the temperature. We, in addition, did an out-of-sample forecast exercise with discarding the last 10,000 years where human activity really started on Earth. And so started 10,000 years ago, which is the blue line, and compared the red line with the blue line. So the forecast, or the sample forecast with and without human interference. I mean, this is 100 years forecast, so obviously they sort of become closer and closer. This is, I think this maybe a bit, whatever, in English to forecast 100,000 years from this data. But what you clearly see is that the blue line is well under the red line. So without any human interference, the temperature should be much lower than it is, and should stay much lower for quite a longer time. For ice, it's sort of the opposite, and the same for CO2. And then we estimated the turning points. We believe that we are now at a turning point for temperature going down, whereas the next ice time period may appear in about 22,000 years, so some time left to buy a warm coat. But in addition, I mean, this is not a very weekly forecast. If you look at the data, it just goes up very quickly and down rather slowly. So maybe it's a bit for a longer time period, but these are sort of the turning points we get with our forecasting method. Right. And this is just the conclusion. Yeah, so thank you very much, and any questions are welcome.